order. Yeah. All right. The first question. Yeah. When we solve some computing problems, sometimes it is a good idea to work on a few cases with small data sizes first. Then we can extend our solutions to the general case. True, because this is a strategy. Basically, I describe a simple, effective strategy in our problem solving. We need to do some experiments. At the beginning, we need to understand the given computing problem, get some experience, or find certain rule for the given question. Yeah, so it's correct. Yeah, okay, yeah. Next question. Is the execution time of a program a stable measure for efficiency? No, not a stable measure. Yeah. The reason I explained in class, for different computer machines, hardware, for different hardware, you may get a, different response times. From the software part, for different implementations, because different programmers, they may implement the same algorithm differently. An experienced programmer can do much better than a beginner programmer, even for the same algorithm, right? So how do you manage the memory? How do you, manage the, storage space, variables, a lot of things could be handled differently, right? Yeah. So for that reason, it's not a stable measure. And later, we come up with a stable measure, counting number of basic operations. That's a stable measure. Okay, yeah. All right, yeah. So that's the first two questions. Yeah. Here, let me just make some comments. Here, in my quiz questions, here, I just want to show you the way I design quiz questions. Yeah. Some of the questions very easy. Yeah. So in this quiz one, actually, we have many easy questions. The purpose, I want to check if you study the materials, video, notes, the materials. So if you study the material, all these questions are so easy. For example, this one, number 2. Yeah. So in our notes, we talk about it. So if you have some impression in the, in the lecture, if you went through the lecture at least once, so it's very likely you have the impression. So many questions are designed just checking if you go through the course materials. That simple. Okay, yeah. Then some of the questions, so when we move to quiz number 2, you will see that we have some challenging questions. Yeah. All right. Question number 3, the fake coin problem, 12 identical looking coins, and we assume the fake one is lighter. Yeah, with this condition, 2-pen scale, the minimum number of weights. Yeah, the answer is 3, right? The answer is 3. Yeah. First, you need to be familiar with the solution. we divide the total number of coins in 3 even groups. 3 even groups. Yeah. 4, 4, 4. Okay. 4, 4, 4. Yeah. The next question, after you get a 4, 4, 4, with 1 weighing, you can determine which one contains the fake. Now, the next question, how to get the fake in 4 coins? Yeah. 1 weighing is not enough. Yeah. So you need a 2 more. So the answer is 3. Yeah. This question is very easy. Yeah. If some of you, if you want to apply the formula, we have the formula, right? For the n coins, log base 3 of n ceiling function. If you apply this formula, you also get 3. Okay. Yeah. Ceiling function of log base 3 of 12. Because you know this number should be 2 point something. Yeah. Because 3 squared is 9. 12 is greater than 9. But 12 is less than, yeah, so I do not have space, 27. Okay, 27, greater than 12. Yeah. So log base 3 of 12 should be 2 point something. Then you take the ceiling function, it's 3. Yeah. Yeah. But if I give, yeah, so here, because 12 is a relatively small number, so you can go through the solution, the whole solution procedure easily. Yeah. But if I give you a question with n relatively large number, for example, n equals 1,000. 1,000. I ask you the minimum number of ways to find the fake one for the worst case. Yeah. So although the minimum, yeah, in the question, I did not say for the worst case, but we always solve the given problem for the worst case by default. So for the worst case, it's the default. Yeah. So by default, for the worst case, okay? Yeah. I may not say it every time, okay? Sometimes I put this phrase in the sentence, the worst case in the sentence, but many times I may not put it in the sentence, yeah. But you treat it as the default requirement. Yeah. So now because this n number 1,000 is too big, so in order to find a solution, the best way, apply this formula. Okay, yeah. And in the midterm, I allow you to use calculator. Okay, yeah. So the, you know, the physical calculator or software sometimes the web-based calculator, right? The web-based I recommend Wolfram Alpha. Very powerful. It's a free. So you go to this website, Wolfram Alpha, so you can do, you know, many complicated computations. Okay. Yeah. All right. So this is question number 3. Yeah. My desktop Zoom ready. So let me connect to my desktop so I can see your questions much faster. All right. Good. Now the next question, easy one. Yeah. Nanosecond C. Yeah. 10 to the negative 9 power, thus number 1 billionth second. Yeah. Also, simple question. If you follow the notes or study, went through the lecture at least once, so easy questions. Yeah. Let me move to the next two. Number 5. Yeah, this one. Okay. Yeah. This one, question number 5, it's also related to our homework question number 24, right? Number 24. Because in that question, we changed to consecutive even numbers.
Record progress.
Oh, sorry. Yep. Mute my desktop. Good. All right. Yeah. So for this question, to solve it, the easiest questions are plugging numbers. Plugging numbers. For example, n equals 1, the simplest case. You can use n equals 1. You can quickly find which one is correct. Plug in. A, plug in 1, 1, 2, 3, 6, 3, right? The answer, but you plug in n equals 1, this gives you 1. Okay, yeah. The second one, 1, 2, 3, also 1. Yeah, be careful. So you get a 1 here. All right. Right, yeah. C, 1, 2, 5, yeah, 2, 5. Okay. Yeah. D, 1, 2, 3. Yeah, that's 1. Okay. So A is gone. A is gone. C is gone. Okay. B and D, you need to check another n equals 2. Okay. Yeah. N equals 2. 1 plus 4, 5. Yeah. But you're plugging B option 2, 3, 4, right? 2, 3, 4. It's 4. Okay. Yeah. So B is gone, right? But you want to make sure D is correct. So 2, 3, yeah. 2, 3, right? 2, 3, it's 6. Cancel out 1, 6. So then 2n plus 1 is 5. Yeah. So D, you get a 5. Yeah. So D is correct. Okay. After 2 rounds of checking, yeah, 2 rounds of checking, yeah, So you get a D is correct. That's simple. Okay, that's simple. Yeah. All right. Now, because after you answer this question, you have the experience. So this solution, you treat it as an experience of yourself. Okay, yeah. So what I mean, this D formula can be used. Yeah, so here. If I do it right, yeah, I have to give you a correct formula. I cannot, just give you a wrong one. Okay, yeah. So here you have the D formula. Can you use it to solve question number 24 in homework assignment number 1? Right? Yeah, you can. Yeah. So this question, you can use it to solve our homework question number 24. Okay, all right, yeah. So here I see a question from Dakota. So then you think it is flow oh, are you talking about, but it's, yeah, let me just go back because you asked this question. Yeah, number 3, not floor. It's seating question, not floor. Why? Because when you have some fraction thing, for the worst case, you need more weighings. If you go floor function, you use fewer weighings. That's not reasonable. That's not reasonable. Yeah, floor function is not correct. Yeah. Seating function is correct. Yeah. Yeah. Remember, if you go back to the notes, remember for arbitrary n, we can find 2 adjacent power of 3. Oh, yeah. So this side should be strictly less than 3 to the kth power of 3, and this side 3 to the kth plus 1. Yeah. In our notes, we use, this range to cover arbitrary given positive number integer n. Yeah. All right. And for this number of coins, we need k weighings. The number of weighings is k. And for this one, we need a number of weighing k plus 1. Okay, all right. So there you have n coins. N coins is at least as many as 3 to the k. You cannot use fewer weighings, right? Think about that. You cannot use fewer weighings. Yeah. When n is strictly greater than 3 to the k, for the worst case, you can only go to its upper end, not the lower end. So that's the reason we need to use the seating function, not the floor function. Okay? Yeah. All right, yeah. Oh, I said the floor function. If you use, oh no. If you use the floor, would it be not the best case? No, not the best case. All right, yeah, but it's a Dakota, yeah, that question, because for the best case, yeah, because you ask this for the best case. You can imagine. For the best case, you can imagine the best scenario. That's the best case, the best overall scenario. All right, yeah, because here we didn't. Oh, sorry. Yeah, for the best. Oh, just a minute. Yeah, you're right. Yeah, this K is the best case. You're right. Based on our current algorithm, yeah, So this is the best case, right? Yeah, because we have an algorithm, right? Because we are talking about the algorithm, divided into 3 even groups. So yeah, that's the best case. Yeah. But if we do not specify which algorithm, then the best case could be different. Okay. If we do not specify which algorithm, any algorithm you can use, then the best case would be one way. Okay. You just pick one normal coin and the one fake coin you put on the scale, then you get it. Because you can assume you are very lucky, so you get the answer, right? So if we do not specify any algorithm, then the best case is one way. But here, because we have existing algorithm, so we're talking about that particular algorithm, then the best case is this K. Yeah. All right, so that's so medicine, know if it's asking for minimum number of weighing on the potential best. Oh, although minimum number, but minimum number must be regarding the worst case. Okay. Yeah. So do not get confused. Yeah. Here. Do not. So here. All right. So we have 2 sets of terminology. One set, best case, and worst case. Another set, minimum, maximum. All right. Here, do not connect them directly. Yeah, some students may like to connect. So the minimum with best case, maximum with worst case, do not do that, okay? This kind of connection is not correct, okay? In general, it's not correct, okay? Separate these 2 sets of concepts, okay? Yeah, so what do we need here? We want to find the minimum number of weighings for the worst case. Is that okay? No contradiction. Do not treat it as contradiction. No contradiction. Okay? Minimum number of weighings, but for the worst case. Okay? Yeah. Yeah. We get by using the sealing instead of. Yeah. Sealing function, you can relate to the worst case. Floor function, for this question, you can relate to the best case. Yeah, that's okay. That's correct. Okay, yeah, for this question. Yeah. All right, I need to move on. All right, yeah. So I try my best. Yeah, try to avoid the confusion. Yeah, here. Yeah. All right. Yeah. So now, yeah, we almost finished this one. Yeah. Yeah. So you just connect to question number 24 of homework number 1. Yeah. Question number 6. Given a polynomial with n+1 coefficients and a variable x for a positive integer n, we only have one way. So this is another easy question to check if you went through the course material, lecture notes, videos. Yeah. False. Yeah. We have 2 methods. The brute force method, or we can call regular method or ordinary method, whatever. Yeah. So another one is Horner's rule. So at least 2 different ways. Yeah. So not only one way. Yeah. Before this class, you may feel only one way, right? Yeah, because you do not know the Horner's rule. Yeah. But after this class, so you should know the Horner's rule. Okay, yeah. So it's a simple question. Yeah. All right. Number 7, fake coin, this time for 4 identical looking, but the fake one, we only know different way. Could be heavier, could be lighter. Could be heavier, could be lighter. Okay, yeah. So you don't know. Yeah. All right. So the question, is it possible for us to use 2 ways to find the fake coin? Yeah. So you need to try a little bit because the number is small, only 4. Okay. Yeah. Yeah. So I hope it's not too hard to get it. Yeah. As I know, the answer is yes. Yeah. 2 ways you can find the fake one. Okay. Yeah. I hope you get it. Yeah. Yeah. So let's say, so we have 4 coins. 1, 2, 3, 4. Yeah. Because this time it's hard to divide it into 3 even groups. You know. Yeah. So let's do our first weighing 1 and 2 here. Okay. Yeah. There are 2 cases. Or 3, yeah, 2 or 3. Yeah. So one case, same weight, another one smaller than the other. Let me just assume. Yeah, like this. Yeah. All right. 1, yeah, both good one, right? Yeah, because this, we know both good. Okay, yeah, both good. So our second weighing, how about we put a good one, 1 must be good, and a 3 here. How about that? Okay, 2 possible cases. If 1 equals 3, then answer number 4 is the fake. Okay, yeah. If different, 1 is less than, we can write different, right? Yeah, we can write different. Because we know 1 is good, okay? 1 is good. So then, this case, yeah, this case, answer is 3. 3 is bad, okay? All right, so here, all right, 1 must be better one, right? 1 or 2 must be better one. Yeah. How about we take one of them? We don't know good or bad. We just put 1 here and a 3 here, but 3 must be good. Okay, yeah, because the better one is in 1, bad in 1 or 2. Okay, so 3 must be good. Okay, so we use 1 and a 3. If 1 equals 3, then the answer is 2. 2 is a better one. Yep, because 3 good one, 1 also good one. So 2 is a better one. So if 1 different from 3, but 3 is a good one, so the answer is 1. 1 is a bad one. Okay, yeah. So although the number is 4, you can see you need to do so much work. Okay, you need to do so much work. Yeah, but I believe you can make it. So even you need to do this much work. After you play around, spend some time, you should be able to make it. Yeah. So the answer is yes. A little challenging, yeah, but you can make it. Okay. All right. Then a very challenging question. So here I do not assign it to you, but if you want to try it, so that would be great. If you want to try it. The same question, but we changed to 12 coins. This time 12 coins. So very challenging. Yeah, very challenging. So it is one of the questions in our textbook. okay? But different way, yeah. But look at what is the minimum number of weighings you need to solve the problem with 12 coins with one fake, but that fake one you do not know, lighter or heavier. Yeah. Just change this question from 4 to 12 and see if you can solve it. Okay. Yeah. Yeah. But this puzzle question, you know, when you have time, you can try a little bit. Yeah. Yeah. But right now, when you prepare for your midterm, so you do not need to spend a lot of time on it. Okay. Yeah. So later, when you have some time, you can try it. Yeah. But at some point, I can give you the solution. Yeah. So I have my PowerPoint notes to show you all the details for the 12 question solution. Okay. Yeah. All right. Yeah. So let's move to next question. Yeah. Yeah, but this time I need to erase. Yeah. The word part. Yeah. All right. Yeah. Question number A, you can see another easy question. If you are familiar with our notes, you have it. Part of just one step in our note. Yeah, I mentioned in the previous slide. Okay. Yeah. So many questions. Yeah. So directly from the notes. Yeah. All right. Yeah, but after this question, you also need to know, yeah, think about, yeah, how special this number 3 here. Why 3, right? Think about that. Yeah. What I mean is, if I change this base number, is it still correct? If I change this 3 to 4, is it possible I can find, so for any given n, I can find the 2 adjacent power of 4 such that we have this, right? Yeah. Or I can change to 5, base 5, power of 5, and so on. Yeah. All correct. All the answers correct. Okay. Yeah. Yeah. So we can use the same way to understand why it is also correct. Okay. Yeah. And this simple fact, you can, although simple, yeah. But when we go from power of an integer to arbitrary integer, this method could be very useful. Okay. Yeah. 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 Because power of 2 case we use frequently. Yeah. 2 to the k less than or equal to n less than 2 to the k plus 1. Yeah. Yeah. Because in our computer science, we use the binary setting frequently, right? Binary setting, that's the most frequently used setting case. Yeah. So this, you know, you need to be aware of this inequality. So when you go from power of 2 to arbitrary n, so there is a good chance you can use this inequality. Okay. Yeah. All right. Yeah. So let me move to the last 2 questions. Question number 9. Yeah. Horner's rule, degree 100, the highest order term, this. How many multiplications do we need if we apply the Horner's rule to a value? 100, the same number of degree, right? Direct application of the Horner's rule. Yeah. Because here, do not, yeah. So there is a little chance, I'm afraid some of you may go to another direction, try to look at a special very special case. Yeah. But here, I said, you apply the Horner's rule based on our standard Horner's rule. Yeah. So even, think about, even you are given a special data, yeah, but when you apply Horner's rule, your solution is always the same as that degree number, okay? Because we don't want to modify the Horner's rule, okay? We just want to use the original Horner's rule, yeah. Even if for a special polynomial, we may have faster solution, but we do not use it, okay? Yeah. For in this question, we do not use it, okay? Yeah. Here I'm talking about repeated squaring, okay? For example, x to the fourth, yeah, x to the fourth, based on our repeated squaring, we needed 2 multiplications. In this one, we do not apply the Horner's rule. We apply the repeated squaring, okay? Yeah, here I hope you do not connect to the repeated squaring, yeah, because I only ask you to apply the Horner's rule. I do not ask you to apply any other techniques, okay? Yeah. All right, last question. In order to derive the Horner's rule for, yeah, here, I'm asking you if you're familiar with the procedure that we derived Horner's rule. We spent a lot of time in the notes from n equals 2, n equals 3, then the general n, right? So the technique factorization. That's only thing. Yeah. So you can see about half of the questions basically just check the materials in a straightforward way. Yeah, our notes materials in a straightforward way. Yeah. All right. Yeah. So we complete quiz number 1. Yeah. Now, yeah, I give you another chance to ask homework questions. So any homework question you want to ask at this point, okay? Yeah, just let me know. Yeah, so I can answer a little bit. If not, then I will move to quiz number 2. Then after quiz number 2, you have a chance to ask homework questions. Yeah. All right, so let me get ready for the quiz number 2. Yeah. R.12. Yeah. Session 1, part 2. Yeah, quiz 2 question. Yeah. Jeanette, we are doing quiz 2 questions. I will go through one by one. Yeah. I know most of you have a lot of quiz 2 questions. Yeah. So here I talk about solutions, but you can type your doubts in the chat box. So when I see it, I will explain. Yeah. So I can see your questions in the chat box. Yeah. So when I see any question, I just explain it. Okay. Yeah. So let's start one by one. Yeah. The first question: to evaluate a polynomial, the higher the degree it has, the more multiplications we need. First, the answer is false. Okay, the answer is false. Then I explain, and then I also clarify. Yeah, because you may get some confusion here. Okay, so I like to first explain why it is false. Second, clarification on certain confusion. I will point out some confusion most of you may have here. Okay. First, we treat it as a statement. So this is a statement. Yeah. When we see a statement, only when it is 100% true, then we treat it as true. Okay. Yeah. only when a statement is 100% correct. It is true. Okay, yeah. So that's our general understanding. So this statement here, the question, can we find an exception? Find an exception. Exception. If we can, it's not 100% true. Okay. Yeah. So that's important. Okay. Yeah. And the answer is yes, we can find an exception. Yeah. The question, how to find? Yeah. Because at this point, I didn't talk about repeated squaring, right? Remember, repeated squaring only when I gave you the hints for homework assignment number 1, I mentioned that. So at this point, you may not know the repeated squaring, yeah. But even if you do not know, yeah, it is still possible you can find an exception here. Yeah. So what's that exception? For example, yeah, Horner, you're based on Horner's rule. Yeah, just a minute. Yeah. All right. So for example, yeah, let's consider x to the 100th power. Yeah. This is a simple example. Yeah. All right. So 100th power. Yeah. We can write it as x to the 10th, then to the 10th. Okay. All right. Yeah. X to the 10th. So you can see, yeah. You can do multiplication. Yeah. If you do not know the best way, it's fine. Okay. X times X. Yeah. You have 10 X copies. So you need 9 multiplications. Then you use X 10th. You do X multiplications. Another round, right? Yeah. Also 10 copies. You need another 9 multiplications. So your answer will be 9 plus 9. Okay, 18. All right. But it is possible you may have a smaller number, but you need more multiplications, right? Yeah. Think about that. Okay. Yeah. Yeah. Smaller. Yeah. So counter example, you may have a polynomial with smaller degree, smaller than 100, but you need more multiplications. That's easy. Yeah. A0 plus A1 X plus, okay. Yeah. I do not need too many. Just the degree 20, right? Yeah. 20. Based on the Horner's rule, this one, we need 20 multiplications. Okay, 20 greater than that, 18. Yeah. But the polynomial, we need more multiplications. Its degree is lower, only 20. The one with higher degree, we need fewer multiplications. Is that a think about, is that a exception? Yeah, we treat it as an exception. Okay, or counter example. Okay, counter example for this statement. Yeah, so this statement is not 100% correct. Okay, this statement, you can say 90-something% correct, but not 100% correct. Okay, yeah, yeah, all right. Now, yeah, how were we to get there without knowing the square? Right, yeah, without knowing squares information, but all right. But this thing, so without knowing square, this thing, you need to discover it. Yes. So this thing, what we are doing here, similar to what we are doing in that repeated squaring. Yeah, but here it's not repeated squaring. It's repeated 10th power, right? It's repeated 10th power. Yeah, something slightly different. Yeah, yeah, yeah. But you need to get this point. Yeah. So that's the challenging part. Yeah, that's the challenging part. Yeah, yeah. Most of you probably couldn't get this point. Yeah, yeah, yeah. But here, I want to make another clarification for the confusion. Now, clarification for the confusion. So what's that? Yeah. First, this sentence, if we treat it as a statement, it's not correct. But when we treat it as a principle, then we can use it in our problem solving. So principle, all right. So here I want to make clarification between principle and statement. Okay, yeah. For a principle, although when you see the wording, it's a statement, right? Yeah, but when we call it a principle, yeah, when we call it principle, okay, yeah, we do not require 100% correct. When we say something is correct in principle, yeah, most of the time it's correct, okay, yeah, because the principle, we use it to guide our problem solving. So then we use principle, yeah. So we can say in principle, or in principle, a polynomial will with a higher degree is usually requires more multiplications than a polynomial with lower degree. So in principle, so most of the time it's correct. Yeah, yeah. When we apply this principle, then it helps. It helps us in problem solving, because based on this principle, we try, what we can do, we try to reduce the degree. We try to reduce the degree to make the problem easier. Right? Yep. Because this principle can guide us to do the right thing to solve the problem. Okay? Yeah. So in other words, when we apply principle, we allow exceptions. Okay? Yeah. Yeah. So although exceptions could happen, but the percentage is low, when the percentage is low, then that means the cost is low. Okay, the cost we spend on those exceptions also low. So we're fine with it. Yeah, because based on this principle, we can take care of 90-something% of the cases. Okay, yeah, all right. Interpret all future quiz tests. Yeah, as principle or statement. Yeah, so for a principle, I have to let you know it's a principle. Okay, if I do not say the word principle, then you treat as statement. Okay, yeah. So if you do not treat, yeah, I have to say things explicitly. Yeah, or in general. Sometimes I say in general. Yeah, when you see in general, yeah, you allow exceptions. Okay, yeah, in general, so not necessarily 100% correct. You allow exceptions. Or in principle, in general, you allow exceptions. If you do not say in general, in principle, then you do not allow exception. Okay? Only when one exception, one counterexample, it is false. Then you treat it as a formal statement. Okay? Yeah, let me put a formal statement. Yeah. So, because in that way, we make our thinking rigorous. Okay? Yeah. Right. Yeah, generally, yeah, not 100%. Yeah. Yeah. So that's compatible with our everyday life experience, right? Compatible with that. Yes. Yeah. So our interpretation, our understanding has to be compatible with our daily life. Now, otherwise, it is wrong. Okay. Yeah. All right. So let's continue. Yeah. All right. Yeah. Yeah, but the next question I need to erase, yeah, some space. Yeah. Yeah, but the response time is still a little slow. Yeah. Yeah. Okay. Yeah. Yeah, the second question. All right. Given a computing problem, if you have this optimal thing to solve it, and you cannot improve it. Here we're talking about you. Yeah, some student before asked me to clarify what's the meaning of you here, right? Yeah, the you could be literal you. Yeah, could be literal you, just yourself, or it could be an abstract problem solver. Yeah, not necessarily yourself, literal. Yeah, it could be any problem solver. Okay, yeah. So even you can imagine the best problem solver in the world. Yeah, it's fine. Yeah, but you can interpret. Yeah. So here the you, you can have different interpretations. Yeah. All right. So if you have an algorithm to solve it and you cannot improve it anymore, then you can say that your algorithm is, yeah, it's false. Yeah. The problem is, yeah, you cannot do it. It does not mean other people cannot do it. Okay. Yeah. Even, yeah, here, even I change it to, yeah. So let me, yeah. Sometimes I can make the statement more confusing. Yeah. Yeah. But usually I do not like to do it in that way. Okay. Yeah. Sometimes I may trick you a little bit. Yeah. But I try to control, do not go too far. Okay. Yeah. Do not go too far. Yeah. Here, for example, if I change this you to the best problem solver in the world. Okay. So the best problem solver in the world. Yeah. Given a computing problem, if the best problem solver in the world have an algorithm to solve it, but he or she cannot improve it anymore, then we can say that this algorithm is optimal. Even that, it is false. Okay? Yeah, even that, it is false. Even the best problem solver in the world cannot solve it. It does not mean a little weaker problem solver cannot solve it, right? Think about that. Yeah, right. Rigorous, since it said cannot improve anymore, seem to be actuality. Yeah, correct. Yeah, your understanding is correct. Yeah, but wouldn't that be rigorous if it was the best problem solver? Yeah, it's slightly rigorous, but still not strong enough. Okay, it looks a little more rigorous, but still not strong enough. Yeah, because how do you characterize the best problem solver in the world? Right? It's not easy, right? Yeah, it's not easy. How do you characterize? Okay, yeah. So because even based on the public opinion, some problem solver, most people treat as the best problem solver, but he or she may not be able to solve certain hard questions, but some other relatively weaker problem solvers could solve that. That could happen, right? Yeah, that could happen. Yeah. So that's one thing. Another thing is we also need to consider future generations. Future generation. Even our current generation, nobody can solve a problem. It does not mean in our future generations, after 100 years, after 200 years, people can solve, right? People can do better. It seems like this can never be true. All right, I will get there. Yeah, Jeanette, yeah, you make a very interesting point. I will get there, right? Yeah, Dakota, I thought you stated in class that one individual could, that's also correct. Rigorous proof that something is optimal if they rigorously prove, right? Yeah, that's also correct. So I will combine. So Jeanette comments, Dakota's comments together, no contradiction, okay? Jeanette, so your comments, Dakota's comments, you both, no contradiction. I will give you, a better interpretation, explanation, all right? Yeah, 200 years, 300 years, yeah. So here, all right, I can give you example from Fermat's last theorem. Yeah, so some of you may heard of that. Fermat last theorem, very famous, big story in math. Okay, so that is very simple. The equation x to the nth plus y to the nth equals z to the nth. This equation has no non-trivial integer solutions. For n greater than 2. Yeah. When n equals 2, that's the Pythagorean theorem, right? Yeah, a lot of solutions, Pythagorean theorem. Okay, yeah, so it's not that. So Fermat, after he read the Pythagorean theorem, he just went one step further, changed the n number to 1 greater than 2, strictly greater than 2. Okay, that his conjecture, he made that conjecture. No non-trivial. What do you mean non-trivial solution? You have many trivial solutions, right? For example, 0 for x, 0 for y, 0 for z. So that's the trivial solution. We do not count it, okay? Or 0 for x, 1 for y, 1 for z. So those trivial solutions, we do not count it. But we only count non-trivial solutions. All right? Yeah. So that's the Fermat's conjecture. All right. But this question is so hard, yeah, after 300 years. Okay, 300 years. It was solved, approximately 1995. Yeah, approximately 1995. So it's a huge story, big story. So that means, if the current generation cannot solve a particular problem or cannot do better, it does not mean the future generation cannot, right? Yeah, all right. So then based on this understanding, then Jeanette said, yeah, so let me go back to Jeanette's comments. Jeanette's comments. Yeah, I need to scroll up a little bit. It seems like this can never be true. That it looks like that, but it's not. Okay, Jeanette. Now I answer your question, and together with Dakota's comments, it's not the case. We can rigorously prove that certain algorithm is optimal. It's possible. Actually, we did it in our finding the minimum question. We did it. So here, the example is, the finding the minimum. Okay. We need n-1 comparisons. Okay, and we rigorously prove it. Okay, we rigorously prove it. Okay, if our proof is correct, it could be wrong, but we need to make sure it is correct. If it is correct, then we don't worry. After 300 years, after 500 years, nobody can do better than n-1 comparisons. Okay, after any number of years, nobody can do better. Okay, so we have that confidence. Nobody can use fewer than n-1 comparisons to solve it. Okay, so it's not the case that people can improve certain algorithm forever. It's not. Okay, so there is a possibility. So here, for some of the questions, there is a possibility that people can get optimal solutions. Then we just prove it's optimal and make sure our proof is correct. Okay, so we have to make sure the proof is correct. After that, then nobody can do better, right? All right, so let me see. We already spent too much time. Let me see. Euclid's algorithm still, Euclid. We will talk about Euclid algorithm soon. What then do we can consider rigor? This question is hard, right? Very hard to answer. Does it have to be approved? It has to be approved. It has to be, mathematically, perfect proof. It has to be a perfect proof. Okay, so here I'm talking about, for Fermat's last theorem. Remember, the first time that mathematician Wales, yeah, that mathematician. Yeah, the first time he claimed he had the proof in 1993, but there was a big hole there. There was a big hole. Then he spent 2 more years to fix that hole. So the proof must be, perfect. Okay, must be 100% correct. Okay, otherwise, if you have even a small hole, you have to fix it. Okay, you have to completely fix it. Then we agree, so your proof is correct. Okay, yeah. So if it's not a proof versus not a proof versus a statement. Yeah, if it's not a rigorous proof, if you just use some explanation, yes, sometimes people may not provide a strong, rigorous proof. Sometimes people may just provide certain explanation, okay, using some real-world experience to explain. So, we cannot treat that as a solid proof. Okay, that could be false. We can say it could be false. Okay, we won't accept it as a formal proof. Okay, yeah, for a statement. Yeah, so proof or disproof. Okay, proof or disproof. Sometimes people can disprove it. Okay, yeah, yeah. So we cannot just say a bunch of people were not right. Yeah, correct. To improve. Let me finish your sentence. To improve it, instead, for it to be optimal, it must be stated that someone was able to prove it could not be improved beyond. Right. Yeah. So yeah. So this understanding. Yeah. So that proof should be very solid, very strong, and we require it a perfect proof. Okay. Even a small error is not allowed. Even a small error is not allowed. Okay. Yeah. 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 So mathematically, yeah. So we need a perfect proof. Okay. Yeah. All right. Yeah. So here already, let me see. So we reached break time. Yes.